Welcome to Lab 3, the magnetic field of a bar magnet. The purpose of this lab is to generate a more numerical understanding of how bar magnets, in this case a magnetic dipole, field interacts with different points in space. We're going to focus on superposition, reducing the Earth's magnetic field impact on a reading as much as possible, and we're also going to see how different distances and angles impact the magnitude of each component of our field. Some fundamental concepts all stem from the Biot-Savart law. Our equation for a magnetic dipole anywhere in space, which isn't as good up close, our equation for distance-dependent law, and our actual graph equation of LNBR versus LNR. And we also need to understand the concept of superposition, since we need to cancel out the Earth's magnetic impact on our readings, so we only get the bar magnet or magnetic dipole's impact. Preview of the results. Our main calculation we needed was mu, the magnetic moment, which is 3.23, and our calculated b-value is 5.60 e to the negative fifth, and our computational model gave us 2.63 e to the negative fifth, which is about a 72% difference, and we'll get into how we exactly got this. For the experiment itself, on our on-axis measurements, using the Magnetometer app, we zeroed the x value, and then we found the maximum x value to locate exactly where it detected magnetic field on our phone. And then we used this to find 5 specific b-values and recorded the distance that it took to get these b-values, and we did each of these 3 times. And for the off-axis, we recorded the distance where b net was 100 microtesla, and then we moved our phone in equal vertical distance to find the 45-degree b-value in our magnetic field components. This is a little visual for our on-axis, perpendicular, and the 45-degree measurements. As you can see, the on-axis phone was horizontal, and then for the 45-degree, we had to move it vertical. The spreadsheet results in the actual graph. Here is the on-axis. You can see that the b of x are all the same for each r group, and the distance is what changes because we had to find what distance gave us that b value. And then here is the linearized graph. For the off-axis results, we had to find what distance b net was at 100 microtesla, and for me that was 19 centimeters or 0.19 meters. And then we also had to calculate the Earth's magnetic field at this point in the y direction, and then subtract that from our total y direction to get just the bar magnet's y direction contribution. And our average b net ended up being 5.60 e to the negative fifth. Calculations we needed for this, we mainly had to calculate mu in order to do our computational model. We looked at the graph to do this, and we found the slope to be the n value of negative 2.73. K, we needed to take e raised to the y-intercept, which happened to be negative 14.254. And since our equation gives us r raised to the 3 plus n, and n is close enough to negative 3, we can approximate r to be 1, since anything raised to the 0th power is 1. And our equation right here, mu is equal to the k value over 2 times the magnetic constant, and that gives us our 3.23 value. As for coding, we can see right here, this is where the magnet is created. This is where we calculated for mu and plugged it in. This is our function for dipole and calculating the b value. This is our scale and distance for visual effects, and these are all our observation points. This is where our objects are actually created. For that on-axis, these are the perpendicular objects. This is for the 45-degree angle b field. And our results, we can see that the on-axis points to the right and the perpendiculars point to the left, and the purple vector in the top right is our 45-degree. Our discussion, when the magnet is far away, the magnetic field approaches 0. This means that the closer it is, the stronger the magnetic field is going to be. And once again, we had a 71.93% difference. Possible sources of error are the distance measurements are not exact, the magnetometer is not completely accurate, and nearby other objects may be interfering. As for the what if questions, what if we hadn't oriented it? All our calculations would be off. More specifically, in the y component, if we had not taken into account Earth's magnetic field, we would never have subtracted it from our total value, and our y component would have been much greater than in reality. And for the x component, if we never zeroed it out, our x component would also be much greater, since we would have had an initial starting one, which would have made the bar magnet seem like it's contributing a lot more. And if we had two magnets, it would theoretically double. However, since they're slightly in different positions, it wouldn't probably actually double, but it would become greater in